Ready to get started with our first scientist talk of the day. I will introduce Tajana and let her take it from there. So Tajana Schneiderman is a PhD candidate in planetary sciences at MIT. She is interested in the intersection of exoplanets and debris disks, belts of comets, asteroids, and dust around other stars. Tajana aspires to be an observational astronomer who dabbles in theory and hopes to further our ability to see other worlds and their atmospheres. When she isn't working to understand nearby planetary systems, she loves to run, knit, and spend as much time in her garden as she can. Thank you so much for joining us today, Tajana. If anyone in the audience has questions for Tajana, either coming in from Zoom or in from the gallery, please use the chat function to input your questions, and we'll get to as many as we can at the end of her talk.
Hi everyone, I'm going to go ahead and start sharing my screen. Okay, well, thank you so much for having me here today. I'm very excited to talk to you all about a topic that is very near and dear to my scientific heart, and that is that of the way that we study planets, exoplanets more specifically, by taking actual pictures of the systems in which they're in. And this technique is something that is called direct imaging. More specifically, I'm looking forward to walking you through sort of the technological developments that are required for us to be able to do this, as well as to talk about one of the problems, or one of the problems we might face when it comes to direct imaging, and that is that of interplanetary dust. Thus, the title of this talk, Peering Through the Dust, which I hope we will be able to sort of mutually agree by the end is an important facet of science that needs to happen. First, I want to talk about how we set about observing things up in the sky. And the way that we do this is by looking for light, primarily. So we want to be able to collect light of some kind. And when we think about how things put off light, some things emit their own light. So this is sort of the case of the sun. Things that are really hot, they're self-luminous, they're producing lots of photons, and we can actually collect and observe this light and learn something about a system. The other sort of case of light being put off by objects that we might think about is that of reflected light, which is sort of the case of our moon. So the moon is not putting off its own light to any significant degree. Most of what's happening there is that it's reflecting sunlight to us that we can observe. And so when we think about the context of observing exoplanets, the things that we really want to see are things that are Earth-like. So things that are sort of small, rocky, still pretty cool. And so the primary form of light that we want to collect here is light that's being reflected off of the surface of the planet. So we can think a little bit about what this looks like in our own solar system. So we might want to say, well, what does it look like if we get a picture of the Earth? Well, here's our famous Earthrise photo that sort of shows this little blue marble suspended in the sky from the surface of the moon as taken during one of the Apollo missions. Now, when we see this image, we can see that there's an exquisite level of detail. We see that there's clouds on this planet. We see that there's ocean because we see that there's glint as well as the fact that it's blue. We see that there's continents. We see that there's spatial variation on those continents. So there are parts of it that are green, indicating vegetation, and parts of it that are brown, indicating that it's maybe desert. And if we wait until it's nighttime, we're going to see that the continents are going to slowly become lit up. So we see that there's some evidence of maybe a technological civilization that is producing light of its own at nighttime that we can observe. And so as an exoplanetary astronomer, if I were to be able to get a photo in this much detail of a planet orbiting another star, I would be over the moon. It would be phenomenal. We would be able to learn a huge amount of information just from looking at it at its surface without having to do more complicated characterization. Unfortunately, images like this for exoplanets are hundreds of years away. What we're going to see instead is something that's more akin to the pale blue dot. So what we're looking at here is an image of the Voyager mission took as it was exiting, or as it was going through the outer solar system, and it turned its cameras back to capture this small pale blue dot. And that dot right there is us. That's the Earth. That's everything. That's our entire world. And this is sort of akin to the level of detail that we're probably going to be able to get for the next decades when it comes to directly imaging exoplanets. So we get a pixel of light. We can learn a lot from that pixel of light, as people throughout this workshop or throughout the day are going to be talking about. But we get a pixel, a dot of light. Slightly updated version of this that I just wanted to put in because I think it's beautiful is this second pale blue dot image looking from the Cassini mission back at Earth from the rings of Saturn. And so here is pale blue dot again. So again, that's the Earth-Moon system. It's a pixel of light. That's what we get. I want to illustrate, though, that even getting a pixel of light is extremely, extremely difficult. And that's because of the fact that Earth is roughly 10 billion times fainter than the sun. What exactly does that mean? Well, it's sort of like you're looking for a firefly that's next to an industrial searchlight. Except for that firefly and industrial searchlight are in Los Angeles, and you're standing in New York City trying to differentiate between the two. Except the firefly in this image is 1,000 times brighter than the actual planet that we're trying to observe. So this is a remarkably difficult problem. And you might rightly ask, how can we possibly see this? How can we possibly see a small rocky planet orbiting another star? Well, the first thing that we can do is, instead of thinking about a reflected light situation where we're looking for small rocky planets that are really close into their host stars, we might think about instead looking for the emitted light of something that's brighter and bigger and further away from its star. And so what we're thinking about here is, okay, well, when planets are really, really young, they're going to produce some of their own heat and therefore some of their own light because they're still forming. So when they're young, they're going to be producing some of their own light. They're bigger, so there's going to be more light, and they're brighter. So, maybe this is a little bit easier of a problem. I'm not saying it's an easy problem, but it is less of a problem than looking for a rocky planet. So the way that we might set about looking through the emitted light of giant planets far away from their host stars is to use a technology called chronography. And so here's a lovely video from NASA JPL that sort of talks about what exactly chronography is. So you'd have a telescope that's pointed at a star-planet system. That telescope is going to be collecting light that comes from the star and planet system. Now, as we collect it, most of what you're going to initially get is going to be the starlight. Now, if instead you put in a chronographic mask that blocks the majority of that starlight and moves the rest of it out to the edges, you're going to be able to significantly dim that starlight. And then if you put in sort of this washer shape called a lyostop, you're going to be able to block out most of the remaining starlight. Now, the planet light is not centered, so as the planet light comes into the telescope, it's not going to be affected by the mask or the lyostop, so you're going to be able to collect it. However, there are atmospheric disturbances when we're observing that make it so that you don't really get a perfect wavefront, which is what we call. So if instead you have a deformable mirror that sort of moves, you can correct that wavefront. So you can correct the light so it's perfectly flat instead of wiggly. And as you do this correction, you're going to be able to increase your contrast to the point where you're going to actually see the planets that are orbiting the star in the system. So this technique of chronography is difficult, but it's doable. To date, we have been able to see giant planets. So these young giant planets far from their host stars, this is something that is a technological marvel thanks to amazing engineers who produce exquisite instruments. But thanks to them, we can see giant planets. Perhaps the most famous example of this is the HR 8799 system. So what we're looking at in this image, the black center is the chronographic mask. So that's sort of the depiction of that mask. And then the 4 bright dots that you see moving are planets. This data was taken over 6 years. So 6 years of repeated observations are able to produce this beautiful GIF that show planets orbiting another star. So we're actually seeing a planetary system, which is just utterly phenomenal. What's even cooler about the system, which is something that I didn't actually know until I sat down to put together this presentation, is that HR 8799 is visible to the naked eye. So if you're in the Northern Hemisphere, put it on your calendar. At the end of the summer, you're going to be able to go out, and if you look for the constellation Pegasus, you'll actually be able to find HR 8799 and know that that star has directly imaged planets around it, which is just phenomenal in my mind. Perhaps I just am too excited by this, but the fact that there are planets is not unusual. We think, you know, on average, every star is going to have at least one planet. But the fact that this star has directly imaged planets is really, really amazing. You might rightly ask, well, why do I really care about these gas giant planets? I'm very curious to see directly imaged small planets. That is, after all, the search for a pale blue dot. Well, I have good news for you. In the not so distant future, we are going to be able to see Earth-sized planets around sun-like stars. This is partially due to improvements in coronagraphs, but it's also due to the proposed missions that include external occulters or starshades. So video preparation again. This is again from NASA JPL. And so Starshade is a proposed mission that will fly alongside a space telescope. And as they get into their orbit, they're going to separate from one another. The Starshade is going to fly in formation with the telescope, a long way away from the telescope, but it's designed in the special petal shape in order for it to be able to effectively block starlight. So instead of actually letting starlight get into your telescope, you have the Starshade to block it from ever getting there in the first place. So here's our lovely planetary system. The Starshade blocks the light from entering the telescope, and then you can see the light that's reflected off of planets in the system. So this is not so far away. A number of missions are proposed to enable Starshade concepts that will enable us to see Earth-sized planets around sun-like stars. But if all of this weren't hard enough, if the technological expertise of engineers who are building Starshade prototypes now and the amazing work that's happened now, if that weren't difficult enough, interplanetary dust is going to complicate our search for a pale blue dot. And this is because direct imaging isn't always straightforward. So here what we're looking at is a very famous system called Fomalhaut. The black at the center is, again, that chronographic mask. And then this Eye of Sauron type of shape is a debris disk. So debris disks are belts of planetesimals, so belts of asteroids or comets that are in systems that collide and produce dust. And what we're looking at here is light that's reflected off of that dust. So it's a very famous debris disk system. And we thought that there was a planet, Fomalhaut b, in the system. And so 2004 and 2006, we saw this sort of pixel that was statistically significant, and we thought, oh, that's clearly a planet. Well, follow-up observations indicate that this isn't actually the case. That pixel that we thought was a planet seems to now actually be the remnant of a collision between two giant objects that produced a momentary burst of dust. And over time, that bright pixel has dissipated and spread out, which indicates that maybe that's not a planet. And so dust in systems is going to complicate it, because if we don't fully understand dust, we're not really going to understand if what we're looking at is a dust artifact or a planet itself. Now, debris disks are remarkably common. These debris disks that I've shown here are things that are extremely bright. And I could go on and talk about some of these all day long, but that's not the point of this talk here. It's just that there is some subset of stars that are very, very dusty, much dustier than our system. But we still don't really have the technology to see things that are more similar to our own system. So you might ask, well, wait a second, we have a debris disk? And the answer is yes, we have several. We have the asteroid belt. We have the Kuiper belt, which is this belt out past Neptune that includes Pluto and is sort of just these icy comets and dwarf planets. And then we have our own zodiacal cloud. So if you go somewhere really dark at night, you're going just after sunset or just before sunrise, you look along the path where the sun is either rising or setting, you're going to see a very faint triangular glow in the sky. And so that glow is sunlight that's being reflected off of the dust particles that are near our orbit. And this is the zodiacal dust. This is not a ton of dust. It's really, compared to these massive debris disks that I showed previously, is really quite small. but even this amount of dust is problematic for direct imaging. Here is a simulated image. Okay, so this is not a real thing. This is just simulations that were done by scientists to try to understand instrument performance. This blob in the lower right corner is a background galaxy. We don't need to worry about that. The bigger belt of material is a Kuiper belt analog that's been brought in a little closer. The two bright specks that you see, those are Jupiter and Saturn, where the bigger one is Jupiter. And then if you look at the center, you see a black mask, which is that chronographic mask. You see a ring of light, which is the zodiacal dust. And then if you look very closely, there's two protrusions that are Earth and Venus. And so even at the level of dust in our solar system, dust is going to obstruct our view of planets and to make it more difficult for us to fully understand them. And we still don't really know how much dust we're going to be able to see, because the technology required for us to fully understand the amount of dust around nearby stars is the same technology we need to see planets that are close into the star, which means we have to prepare now to deal with dust. And so that's what I do. I work on understanding dust, work on understanding the context of that dust and planets in the system, so that way, as time moves forward, we can understand the dust to understand the context that a planet is in, and therefore have the best possible chance of fully characterizing and understanding planets. With that, I'm really happy to take any questions.
Thank you so much, Tajana. I think you can probably exit screen share so we can have a little conversation. Thank you so much for your wonderful talk. Tajana's talk inspired the name of our art exhibition on view, Exoplanetary Dust, as kind of alluding to the fact that there's still so much to be known. And even though we can see certain things, we really still can't access them. That's a very common problem in science, and it's something that art can handle very well. Just to start off, we had a question from the audience about the pale blue dot picture. Roughly, if you know off the top of your head, how far away is that picture of Earth?
Yeah, so that's out at about the orbit of Saturn, which is sort of, 10 to 12 AU, I think. I should.
Okay, in 10 to 12 AU in layman's terms would be something like...
So an astronomical unit, or AU, is the distance from the Earth to the sun. And so that's about 7 light minutes, or 8 light minutes. So we're sort of talking, it takes a decent amount of time for light to travel that distance.
Yeah, great, thanks. So one question which we came up with to get talking about art and science for you is, I'll lay the context. In the early 1920s, Cubism, if you know anything about the Cubist movement, many artists participated in it, and many scientists were actually interested in Cubism, including physicists like Niels Bohr. Cubism helped him imagine quantum theory when he was kind of comparing the behavior of electrons with Cubist paintings. And at the same time, physics was really in rapid development and has been a large source of inspiration for for artists, including artists such as Dali, who was really interested in nuclear physics. And so we were wondering, as a scientist in astronomy, kind of where do you find that art-science intersection? Where do you find the art in your research, if you do at all?
I think that some of the intersections of science and art are that both can be very profoundly beautiful and profoundly moving. And so I personally find whenever I can produce a really cool figure or something that tells me something new about the universe as we know it, I find that to be very inspiring in a way that I find a lot of artwork to be inspiring. And so I think that for me, being able to, I think that science and art are both ways of looking at the universe. And so science just happens to be the one that I spend a bit of time in.
Well put. And yes, just as a reminder to the audience, we have some time for questions, so please input them in the chat box of your platform, whichever platform you may be on. to talk a bit more about kind of what can happen with art and science, specifically, so many of these images of space that we see, while most people understand they're kind of heavily edited for visualization purposes, nonetheless, they are images of space and they're taken and manipulated for scientific purposes, but they often get elevated to this realm of art, like that picture of the, the Crab Nebula, or of I'm blanking on the name of the pillars. There are just these stunning images that we see. Even the pale blue dot, really, people have that as a poster on their wall for aesthetic reasons and because of the science and the story the science tells. So what's your take on kind of when scientific images become so popular that they kind of enter the realm of art?
I think I think that they're beautiful, and so I think that this concept of natural beauty being able to be an inspiration for it is really important to keep in mind here. I sort of also think that we can, as scientists, we can learn a lot from better visualization of the things that we're looking at. So even in the pillars of creation, a lot of times, you're right, things are heavily edited. Sometimes you can see the X-ray galaxy, so the galaxy in X-rays rather than sort of invisible light as we might see it. And so being able to apply those different filters that allow us to see things in ways that we can't see with our eyes because we didn't evolve to see X-rays is something that I think is quite important.
Yeah, that's a really good point. Other questions coming in. How much of a hazard is interplanetary dust to spacecraft, particularly telescopes and future exploratory missions?
Yeah, so you can definitely see on different spacecraft where it's been impacted by dust. The thing that's really important to keep in mind is space is really, really big, which might sound sort of, like the understatement of the year, but when you think about dust, as we showed, or as I showed in some of these images, dust can be as bright as the planets you're interested in studying. Dust is really, really tiny. So we're talking about things that are, the width of a human hair. So they're super tiny, but there's a lot of them. Even though there's a lot of them, though, they're not super tightly packed. So it's not like, you would go out and if you stuck your hand up into space, it's not like you would necessarily be automatically hit by something. One of the calculations, one of the back of the envelope calculations I did sort of my first year of graduate school was to realize that dust, there's on average about 1 particle per square kilometer.
Okay. So yeah, in theory, you could kind of navigate in such a way that you may never hit any dust.
Not necessarily. You're still definitely going to hit it. It depends on where exactly you are. There are some places in space that are less dusty than others. One of the big issues right now is thinking about sort of space debris, so space junk that we've left up there, where that does produce dust, and collisions between big things produce a lot of small things. And so if we artificially inflate the number of particles that are in space, they're moving very quickly. And so even if they're tiny, they can cause a lot of damage.
That's a great point. Another question in from the audience. When we see images of space, we don't typically see the stars represented, for example, the moon landing pictures, but we can see them in the night sky with our eyes. Lydia is wondering, why is this? Is this just a trick of the camera versus a trick of the eye?
Yeah, this is actually a really good question, and I don't know the answer to this off the top of my head, which seems silly, but there it is. I think if I had to hazard a guess, I would say that it's probably about the fact that you're not really, with a camera, you're not looking for long enough to collect enough photons from the stars, and our eyes are actually much more sensitive than a camera is. And so I would just say that I think that it comes down to the fact that our eyes are much more sensitive than a camera. So if you set up a camera on a tripod on the moon and collected for longer, so you were collecting more photons, you would see the stars. But if it's a really short shutter burst, you're just not going to collect enough light for them to be able.
Yeah, that makes sense. And what has been one of the most surprising discoveries in your research?
So I think, as we mentioned, I work pretty broadly on debris disks. So some of what I do is this direct imaging, but some of what I do is actually studying debris disks as a class. And I'm looking at a system where we're pretty certain we're detecting gas that's been produced in the aftermath of a giant impact. So something like the impact that formed the Earth and Moon system in another system. And so that is something that I just think is really phenomenal, because if what we think we're seeing is true, it would be the first of its kind.
Wow, that's really exciting.
Yeah, fingers crossed.
Fingers crossed. Well, that is about all the time we have for today with you, Tajana. But again, thank you so much for sharing your research and insights on exoplanetary, all things exoplanetary and all things planetary dust. It's been lovely to have you here.